interesting lecture by Professor Roy Ozeri. He is the Vice President of Weizmann Institute of Science. The lecture will be on quantum computing more than a technological revolution. This webinar is a part of webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within Engineer Association as a cluster of photonics entities. Our mission is to deepen the knowledge in photonics and to encourage cooperation both within Israel and with photonics entities in the world. We are holding a weekly webinars on various photonics topics. We invite you to sign up to follow the activities we hold, which are published in our monthly newsletter. Per your request, the newsletter will be delivered to your mail. My name is Shlomo Glaser, I am the manager of Photonics Israel. With your permission, few words in Hebrew. יש התפתחות מאוד מהירה בתחום הזה של פיזיקה וטכנולוגיות קוונטיות. אנחנו רואים אותם כבר במחשוב, בתקשורת, בניווט, גלאים, מדעי תאוצה ועוד. עבור כל הטכנולוגיות האלה יצטרכו בהרבה מאוד מהנדסים בעלי ידע מתאים, ולכן כדאי להיכנס וללמוד את התחום הזה. יש לו פוטנציאל כלכלי רב, והוא מייצר הזדמנות לתעסוקה ולהתפתחות אישית. אוניברסיטת בר אילן למשל, היא תפתח בשנה הבאה תוכנית של קוונטום אינג'ינירינג, ובארצות הברית התוכניות האלה כבר קיימות. אנחנו היום נמצאים בהרצאה הרביעית בתחום הזה, ויש לנו עוד 3 הרצאות בקנה. אנחנו שוקלים פתיחה של קורס למהנדסים בשם מבוא לפיזיקה וטכנולוגיות קוונטיות. אני מדגיש, קורס למהנדסים, באמצעות המשוב לוובינר הזה ולאלה שיבואו אחריו, נשמח לשמוע את מידת העניין שלכם בקורס הזה. עוד דבר אחד, אני מאוד ממליץ לקרוא ספר, כתוב בעברית, שנקרא פיזיקה קוונטית מבוא, כתב אותו דוקטור בועז תמיר, ומי שיקרא אותו ייכנס לקורס שאנחנו מתכוונים לפתוח עם בסיס מאוד רחב. פרופסור רועי עוזרי received his PhD degrees in physics from Weizmann Institute of Science. He conducted research in the field of ultra-cold atoms. Professor Ozeri focused on one of the greatest challenges in developing quantum computers, which is finding ways to mitigate the effect of noise on quantum systems. Since quantum information is extremely fragile, noise is the largest nemesis of quantum computing. Professor Ozeri, the floor is yours.
Thank you very much, Shlomo, and thanks everyone for tuning in. Let me share my screen. Do you see it?
Yes, we see it.
Good. So what I'd like to tell you about today is quantum computing and why I believe quantum computing is a significant technological revolution. I think it's a new paradigm in computing theory as well as practice. And also, you know, I'll tell you why I think that it's more than a usual technological revolution. What you see here is an image of 8 individual atoms. These are ions, atoms that are lacking 1 electron. We use each one of those as a quantum bit or qubit, as we call them. So this is a quantum byte, and that's an image taken from the quantum computer that we have here at the Weizmann Institute of Science. Below the image of the trapped ions, you can see an image of the chip that we use in order to build this computer. You know, typical sizes here are hundreds of microns, and this is a stack of fused silica wafers that are coated with gold electrodes. Okay, so let's start. So in order to explain what quantum computers are, what I need to do is give you a crash course in quantum mechanics. And if we had, you know, 2-3 hours, we'll go through all the equations here, but because Shlomo said I only have 45 minutes, instead of going through the math, I'll try to give you the focal point or the center of quantum mechanics and why it's relevant for computers. So I think, you know, when you study physics in high school, you study classical physics and you study the laws of Newton. The laws of Newton, if you like, are the operating system of all objects that are our size, that are, you know, are the size of a football, if you like, or the size of a person. But it turns out that if you go to the microscopic world, you go to the world of atoms and electrons and molecules, the operating system, the mechanics, the set of laws that governs the behavior of these particles is very, very different. So what is the difference between, two, if you like, two balls? One ball is a football, and the other ball is almost the same. If you look at individual atoms, especially if they're not excited, they're very spherically symmetric. So unlike this cartoon of electrons circulating in very clear orbits around the nucleus, an atom is very, very spherical. It's very round shaped. So what's the difference between these two round shaped balls? The main difference between them is that this guy here is probably 9 orders of magnitude smaller than this guy here. So what is the difference in terms of behavior? And to look in the difference in terms of behavior, let me categorize phenomena in nature under 2 main categories. One main category is particle-like behavior. Many objects in our world behave like particles, so very similar to the group of pebbles that you see here in this image. Particles are very simple objects. To begin with, particles are local. These pebbles and the football that I've shown you before behaves like a particle. They're local. They can be either in one place or another. The other unique feature of particles is that they add up very simply. If I have one particle and I add another particle to it, I have 2 particles. I'll add another particle, I have 3 particles. Very simple to add up or subtract particles. Another phenomena that we have in nature, and many, many objects, if you like, in the world fall under this category, is the phenomena of waves. And you can see here an example of a wave that is generated when we throw one of the pebbles that you've seen before into a pedal of water, for example. So waves are almost everything particles are not. To begin with, waves are non-local phenomena. Where is this wave? There's no one position where that wave is. That wave is really spread all over that pedal of water. The other thing with waves is that unlike particles that add up simply, waves add up in a non-trivial way. Waves interfere. What do I mean by that? And you're all coming from the optics community, so I'm sure you're familiar with the phenomena of interference. I can think of waves as periodic objects that have mountains and valleys and mountains and valleys. And if I take 2 such objects, they can add up in a way where a mountain would meet a mountain and a valley would meet a valley, and then I'll get a wave which is twice as large. In this case, the interference would be constructive. I can also make them meet such that a mountain meets a valley and a valley meets a mountain, and then they null each other, and I'll get no response. And in this case, the interference would be destructive. So in the macroscopic world, we're used to thinking about big objects as particles, but it turns out that when we go to the microscopic world, and I'm sorry, before that, I wanted to show you some nice pictures of waves that you might be familiar with. What you see here is a picture taken from the space station of diffraction of waves through the narrows of Gibraltar coming from the Atlantic Ocean into the Mediterranean. That is an example that even when you try to localize wave into the 13 kilometers of Gibraltar, you'll see that once the wave goes through that narrow, it diffracts and it occupies all of space again. Waves do not like to localize. They want to diffract and non-localize themselves over space. That's another example of waves which are scattered off of a group of islands. In this case, these are islands south of the UK called Scilly Islands. And you can see that the reflections of waves from the islands interfere in this region here. And in some cases, you can see constructive interference that gives larger waves, but in other cases, you see destructive interference that gives lower waves. Right, so we're used to thinking about waves as propagating through medium, but it turns out that, that even when we go to the microscopic world and we look at atoms or electrons, they suddenly start behaving like waves. They become non-local. They occupy all of space, and we have to describe them in the language of waves. What you see here are images of ultra cold atoms, very, very cold atoms. We create images like this in labs at the Weizmann Institute all the time, and you can see that when we let the atomic wave occupy all of space, and when the wave, for example, reflects from two different objects, we get interference patterns. So atoms really behaves very similar to waves. They behave very similar to laser fields. And when we think about atoms, when we think about things that, at the face value look like particles, but they do behave like waves, that really puts us in strange situation, and it forces us to ask interesting questions. So for example, if you're from the optics community, you're all familiar with the notion of interferometers. Interferometers are machines that I can inject laser light into those. Here I have a mirror which is partially transferring and partially reflecting. The laser light wave would, part of it would be reflected, part of it would be transmitted, and then I'll have two mirrors that would direct this wave again into a 50-50 beam splitter. Part of that wave can exit through port A, and part of that wave can exit through port B. And I can ask the question of whether the wave went through path 0, the lower path, or through path 1. And the answer would be, of course, that it went through both. How do I know it went through both? I know it went through both because it'll interfere on the way out, going to port A or port B. That question would become even stranger if I'll ask myself the same question on a single photon, on a single particle of light. In that case, I'll have to reach the conclusion that this particle of light went both through path 1 or through path 0. It actually went through both paths, even though I think of a single photon, a single particle of light. I can also ask the question of whether this wave would exit through port A or whether it would exit through port B. The answer is the interference between the two paths would determine on whether the interferometer output is on port A or on port B. The phase difference between these two paths would determine whether destructive interference happened in A and all the light, meaning that every photon would go through port B, or that the phase between these two paths is such that B is destructively interfered and all photons are going through port A. So when I go to the microscopic world, I have no choice but to accept the idea that atoms behave like waves and therefore can be in several places simultaneously. Atoms, when I push them through an atomic interferometer, Shlomo mentioned a few minutes ago that we're able to use quantum technologies in order to measure accelerations. One of the most sensitive, if not the most sensitive machine today to measure accelerations is an atomic interferometer, which means that if I push an atom through an interferometer, remember it's a wave, I can drive it through an interferometer, I have no choice but to accept the fact that when going through the interferometer, the atom was simultaneously at path 0 and at path 1. And in fact, it's not just position. Any physical reality I can think of and attribute that physical reality to atoms, these atoms can behave like waves and exist in a wave function that exists in all these physical states simultaneously. So that interferometer, if you like, doesn't have to be in real space. It can be in another type of space. I can give you another example using light. You can also build an interferometer where the two arms of the interferometer would be the two polarizations of light. Okay, so in this case, in the interferometer, the light doesn't go through different physical paths, so it doesn't go through different places, but it does go through different paths in configuration space. One part of the photon would be in polarization pointing upwards, and another part of the photon would be in a polarization pointing, directing in the horizontal direction. So any physical reality I can think of, atoms can exist in all these physical states simultaneously, like waves do. We call this principle the superposition principle, but that's really just, if you like, the professional physics term that we use in order to describe that phenomena. And we also have a mathematical way to describe it. So, for example, if I have an atom, which is in an interferometer that sent one part of the atom to Tel Aviv and the other part of the atom to New York, I'll write that superposition as some alpha. That's a complex number that multiplies the physical reality of the atom being in Tel Aviv, plus beta, that's another complex number, multiplying the physical reality of the atom going to New York, okay? Alpha and beta are really the wave amplitudes, okay? And the wave amplitudes, you know, if you remember from optics, the amplitude square is the intensity. In quantum physics, alpha absolute value squared and beta absolute value squared are the probabilities, meaning that if I perform an experiment and I measure whether the atom is in Tel Aviv and New York, and I'll say a word about that shortly, I'm going to find it in Tel Aviv with a probability alpha squared and in New York with a probability beta squared. That means that alpha squared plus beta squared equals 1. And that's why geometrically I can represent the state of that superposition as a vector with a sum. So, you know, alpha and beta are complex numbers. There are really 3 independent parameters in this absolute value square sum, which means that I can describe my superposition state as a point on the surface of a unity radius sphere, where one point, let's say the North Pole, would correspond to Tel Aviv, the South Pole would correspond to New York, and any other point in the sphere would be a superposition of the atom being both in Tel Aviv as well as in New York. So what do I mean by measuring whether the atom is in Tel Aviv or in New York? So consider the situation of the interferometer that I described a few minutes ago. What happens if I now put photodiodes in these 2 interferometer paths and I measure the intensity of light going through point path 1 or path 0? Notice that in this case, these 2 paths cannot interfere because they terminate at the photodetector. If I now send photon by photon through the interferometer, either this photodetector would click or this photodetector would click, which means that when I measure, I will measure the photon either at 0 or at 1, even if I started the photon at a superposition of 0 and 1. The probability, again, of measuring the photon at 1 would be alpha squared, 0 would be alpha squared, measuring at 1 would be beta squared, for that matter. And if this is a 50-50 beam splitter, that would be 50% probability measuring it here and 50% probability measuring it here. How does it look in the lab? So, you know, if I take my atom and I prepare it in some superposition, and I change the superposition according to a length of some control pulse, what I see in the lab are clicks on a detector. These could be analogous to the clicks of the photons on the photodetector. Initially, when my superposition is at 1, I'm only going to get clicks at the photodetector, which sits on the path 1. But after I, if you like, rotate my my vector on the sphere and prepare superpositions, I start getting clicks on the 0 detector. After a while, all of my superposition is in 0, and I'm only going to getting clicks at 0, and so on and so forth. In order to see the superposition oscillate from the north pole of the sphere to the south pole of the sphere and vice versa, what I need to do is repeat the measurement many, many, many times and get statistics in order to extract the probabilities. What you see here through the ray data is the probabilities. Okay, so this is the control we have over a superposition in our lab. So I think this at this point it pretty much concludes the introduction that I wanted to give on quantum mechanics. At this point, you could ask, what does all this have to do with computers? Why does quantum superpositions has any effect on computers? And the first ideas along this line came from this gentleman at the top left corner of the screen, Richard Feynman was an American physicist of Jewish origin. He was a physicist at Caltech. He received the Nobel Prize in 1965, I believe, for developing the quantum theory of electrodynamics. If you like, the basis for us using the term photons to describe the particles that populate electromagnetic waves. He was quite a character, actually. He had a few very entertaining books, autobiographic books about his life. The most famous one is called "You're Surely Joking, Mr. Feynman." It's a very entertaining read, and I recommend it. And towards the end of his life, in the mid-1980s, he started thinking about what would be the physical limitations to the operation of computers. And he came out with a notion that quantum computers would be supercomputers. And the basic argument is the following. If I have, information is digital in computers, and I encode it in bits. Let's say I have one bit of information, one physical switch that represents either 0 or 1. That switch can be in either one of two states, 0 or 1. Let's say it's a capacitor which is charged or discharged. It can be a magnet which is pointing north or south. Any type of physical switch you would like to think of. A quantum bit can be simultaneously at 0 and 1. A quantum bit can be in a superposition of 0 and 1. What happens if we have two such bits? So two physical switches. These two physical switches can be in one out of four possible physical states: 0, 0, 0, 1, 1, 0, and 1, 1. A quantum two-switch system can be in a superposition of all these four states simultaneously. If I have three switches, these three switches can be in a superposition of all 8 different possibilities of 3 switches, whereas 3 classical bits would have to be in one out of these 8 possibilities simultaneously. The law is, as you probably know, and if not, you can guess, the number of physical states that a classical system can be in is 2 to the power of the number of switches. A quantum rendering of this machine can be in all 2 to the power n possibilities at once, in a superposition of all 2 to the power n possibilities. And anyone who knows anything about exponential scaling knows that you don't need a large number of bits for that number of possibilities to be mind-blowing. For example, if I have 100 bits and the computers you use have physical realizations of gigabytes, of tens of billions of bits, only 100 bits can exist in one out of 2 to the 100 different physical states, whereas 100 quantum bits can exist in 2 to the power of 100 possibilities, a superposition of 2 to the power of 100 logical states simultaneously. That's a huge computational power if you use it right. The advantage of quantum computers over regular computers can be exponentially large, meaning that if I had to go through all the different possibilities, input possibilities of the classical computer, I have to go through 2 to the power of 100 different possibilities. That's a number which is larger than the number of atoms in the universe. There's just no way I could go through 2 to the power of 100 different possibilities, even if I had the largest supercomputer in the world today. The largest supercomputers in the world today can probably go through 2 to the 60 possibilities in a day or two. A quantum computer, in principle, could scan through all these 2 to the power of 100 states at the same time by preparing a superposition, a wave that would be extended over all these 2 to the power of 100 possibilities. So if the supercomputers, the strongest computers we have today, that's a picture of the IBM Summit, which I believe is in Lawrence Livermore Lab in the US. That's, I don't know if it's the strongest computer publicly known in the world today or in the top 5, but anyway, it's one of the largest. And the reason it's such a strong computer is because it works in parallel with a few tens of thousands processors. And it occupies the area of a little basketball court and the power of a small power station, a few megawatts of power. A quantum computer is a much more modest device. It uses one processor, but it computes in parallel in many, many physical states. It uses superpositions that extend over many, all the possible physical states that the computer can be in. And I'll say a little bit more about that in the following slides. Before that, I'd like to say that very similar to a classical computer, in order to be able to prepare these huge superpositions and control, if you like, perform all the quantum logical operations, we need a universal gate set. So very similar to classical computers, these are machines that execute Boolean functions. Boolean functions are functions that operate on long binary words. When a computer operates on these long binary words and executes these Boolean functions, it doesn't do that by customing the Boolean function ad hoc for that special word. It does that by concatenating, or by putting together gates that are part of a universal gate set. So in classical computation, you can show that any Boolean function can be executed, for example, by performing one-bit NOTs. One-bit NOTs take the 0 into a 1 and 1 into a 0. And by performing, for example, exclusive ORs or controlled NOTs. Controlled NOTs are gates that perform a NOT, a one-bit NOT on the target bit, conditioned on a control bit being at 1, and it doesn't do it when the control bit is at 0. Using these two gates, we can execute any Boolean function we would like. In the quantum world, we have a very similar set of quantum gates. For example, an analog to the one-bit NOT would be a rotation. If you remember, we said we represent a single qubit superposition as a point on the surface of a unity radius sphere. An analog to the one-bit NOT would be a rotation of that point. In other words, preparing arbitrary superpositions of a single qubit, the full NOT would be rotating from the north sphere all the way down to the south sphere of that representation. A controlled NOT would be very similar. It'll take a 0 to 1 in that physical state, conditioned on the target bit, conditioned that the control qubit is at 1. So if the control qubit is at 0, the state of the target bit does not flip. Whereas if the control bit is at 1, the state of the target bit does flip. And that type of universal gate set can lead to a non-trivial phenomena, which is the result of correlating the superposition of two quantum particles. We call this phenomena entanglement. In Hebrew, it's called matzav shazur. And the idea is roughly the following. If I take, to my two qubits, and I initialize my target bit to 0, and I prepare my control bit in a wave which is equally spanned over 0 and 1, so my control bit is an equal superposition of being in the 0 state and the 1 state, and I apply a controlled NOT, my target bit would only flip in the part of the superposition that the control bit is at 1. And after that, I'm going to get a wave. That's a 2-qubit wave, and it describes the state of either these two particles being at 0 or these two particles being at 1. And in this case, I don't know at which of these two states the particles are. I only know that with 50% probability, I'm going to find both at 0. And at 50% probability, I'm going to find both at 1. And I wouldn't be able to know until I measure. And these particles, after I entangle them using this controlled NOT gate, are not necessarily together. I can take one of them, leave it on Earth, and the other one sent to the moon. And still, they wouldn't know if they're at 0 or 1. They'll occupy both possibilities. But if I'll measure the qubit which is on Earth and find it to be at 0, the qubit on the moon would immediately find itself at 0 and would not occupy 1. This is a very confusing phenomena, because somehow the qubit on the moon knows that I measure the qubit on Earth and arranges itself in the corresponding state. Whereas we know that, to transfer information from here to the moon, there's a delay, which depends on the distance of the moon and the speed of light. So I can't communicate the state of the qubit on Earth to the moon immediately. Nevertheless, the qubit on the moon immediately correlates itself with the measurement outcome of the qubit on Earth. The first person to point to this anomaly was Albert Einstein, together with Rosen, who later became a professor at the Technion. They thought that this is actually a proof that quantum mechanics is incomplete. Nevertheless, they were wrong as far as we know, and this is really a valid description of reality. So just to sum up on the inner workings of a quantum computer, the way we think of a quantum computer, let's say with 100 qubits, is as an interferometer with 2 to the 100 different paths. 2 to the 100 different paths means that I have an interferometer where light really has to go through an exponential number of trajectories, and I cannot measure during the computation where in these trajectories my quantum computer is. The wave has to extend over all trajectories, but at the end I need one answer. And to get one answer, what I need is for all paths to interfere constructively on a single output, because I'm looking for a single computational result. I'm looking for a single answer. That means that all 2 to the power 100 minus 1 outputs need to undergo destructive interference, and the computer cannot output through these ports. Only a single output, the answer to my computation, needs to undergo constructive interference, and all the waves in the quantum computer have to coherently build up for the quantum computer to output at the right output, at the answer of the computation. This idea is an idea that consolidated following Feynman's suggestion roughly at the early to mid 90s. So it's already 30 years old. And during these years, a few dozen algorithms were conceived in which, if you use a quantum computer and use the phases of different waves correctly, you'll be able to solve problems that classical computers simply cannot cope with. And I'm listing here 4 of those really arbitrarily. If you want to see an exhaustive list of quantum algorithms, I would send you to this internet link here, quantumalgorithmzoo.org, which I believe is maintained by NIST, but I'm not sure. So for example, the factoring algorithm, which is perhaps the most famous quantum algorithm because it would enable a quantum computer to break through the most secure cryptographic methods we have today. The task here is to take an n-bit integer and find the prime factorization of that integer, would perform at the speed, or the number of steps you'll need to finish this calculation would go like n cubed, where n is the size of the binary input into that computer. Whereas the best classical computers we have, algorithms we have, would solve this problem in 2 to the power of n over 4, which means that the speed up we get is exponential. Another example is a random search algorithm where we want to find a specific input by Oracle query. In this case, this is an NP-hard problem for those of you who know what NP-hard problems are. Here, the gain we'll get is only polynomial, but still, instead of needing 2 to the power n different queries, we need the square root of 2 to the power n queries in order to find the right input. And there are 2 other examples here where you get super polynomial speed up. Actually, one of the interesting applications of a quantum computer is to simulate quantum systems. The simulation of quantum system is incredibly important in chemistry, in molecular synthesis, in material science, in the design of electro-optical devices. We cannot simulate quantum systems for the very reason that I outlined now. If you want to simulate quantum systems, you need to follow superpositions of 2 to the power n options, where n is the number of degrees of freedom of your problem. Whereas if you have a quantum computer, you can really do that with a polynomial of n number of steps. So again, the speed up, the advantage that you get with a quantum computer is exponential. And in the last decade or so, people have been working very hard and also successfully to harness these mathematical problems into different applications that come, as I said, from the world of molecular simulation, optimization problems, machine learning, which yet is another big optimization problem, in cryptography. People estimate the market behind these to be there's a McKinsey report from last year, to be at the tens of billions of dollars annually, even with a modest size quantum computer. So there's a very big and very large economic and financial incentive to build these computers, as well as strategic and security incentive to build those. Just to give a quick remark on complexity classes in computation, for those of you who are familiar, the problems that classical computers can solve today is a class of problems called P. P means that you need a polynomial number of steps to solve the problem. And it's a polynomial of the number of bits you need to encode the problem. There's another class of problems called NP. NP means non-deterministic polynomial. This is the class of problems that, given a solution, you'll able to verify that the solution is correct in polynomial time. Now, there are many problems that we can check that the solution is right, but we cannot solve them in polynomial time. So NP contains P, but it's much larger than P. Today, people believe that quantum computers are stronger than P. There are more problems that we can solve in polynomial time using a quantum computer, but it's still smaller than the full NP class. So people believe that bounded probability quantum polynomial computers are classed somewhere in between P and NP. Okay, so we spoke a little bit about the way quantum computers work, but we spoke about the way quantum computers work ideally. In real life, quantum computers need to work in the face of imperfections and noise and errors. And if you remember, if you guys come from the photonics community, you know how challenging it is to maintain an interferometer stable under field conditions. Now, we're not talking about a regular interferometer. We're talking about an interferometer that has, if you're using 100 qubits, 2 to the power of 100 different paths. So that means that they're very susceptible to phase noise. You need to maintain phase stability over an exponential number of different paths. And it's also very hard not to measure. We said that if we put a photodiode in one of these paths, we'll measure where the photon is, and interference would go away. The quantum computer wouldn't work. It doesn't have to be, a photodetector. A speckle of dust can fly through one of these interferometer paths, and if the photon is scattered from that particle of dust, that's it. The quantum computer is done. So it's very difficult not to measure, and it's very difficult to maintain the phase stability over all these paths. And that's why it's very difficult to build in real life quantum computers. In other words, quantum computers are exponentially more susceptible to errors. This is also the reason why we believe we don't see spontaneously, we don't see naturally superpositions of macroscopic objects. We don't see superpositions of a cat being alive and dead simultaneously. That is because a cat is made out of many, many degrees of freedom, many, many atoms. And in order for that wave to interfere in any sensible way, it'll be a huge control problem to try and stabilize the phase over all the different possibilities of interference paths. So quantum computers are extremely sensitive to noise, and that's why trying to get to quantum computers that are sufficiently large in order to beat classical computers, in order to demonstrate the solution of one of the algorithms I've shown you before, in a way that a classical computer cannot. So demonstrate the exponential speed up, or the quantum supremacy, if you like, of quantum computers over classical computers is a very, very difficult task. The thing that really helps the community is the fact that with an exponential speed up, You don't need that many qubits in order to build a machine that would be impossible to simulate by a classical computer. We've seen two very nice demonstrations from the last year. A year and a bit ago, Google announced quantum supremacy with a universal quantum computer made out of superconducting qubits, and they used 53 qubits in order to demonstrate that quantum supremacy. And really last week, the National Laboratory at Haifei demonstrated quantum supremacy using a photonic-based quantum computer. In this case, it was more an application-specific quantum computer, so if you like, a quantum ASIC, that used 100 photon qubits to again demonstrate quantum supremacy. I'm not going to say much about it. Both these problems are not very applicative problems. They're problems that were tailored in order to demonstrate quantum supremacy. They're both sampling problems, so they're statistical problems. They were both built with computers that are still noisy, and we call these type of computers NISQ, noisy intermediate scale quantum computers. And the last 5 minutes of my talk, if you like, I would like to say a few words about how we perceive this field moving forward. It's clear that if we keep on working with noisy quantum computers, we're not going to get far because we're exponentially more sensitive to noise. So our exponential speed up is really compromised by exponential susceptibility to noise. The solution really is to use to reach fault tolerance, to reach resilience to errors through a notion called quantum error correction, which I would like to briefly describe. So errors are not an invention of quantum information science. Errors are very prevalent also in classical information. For example, if you're using the radio noisy line, B is very hard to distinguish from C, and that's why a solution is to encode this into a longer word and use redundancy. So B would become Bravo and C would become Charlie. Now, if I say Bravo or if I say Charlie, I use much longer words than necessary, but Bravo and Charlie are much easier to differentiate over a noisy radio channel. In the digital world, we use error correction very often. Perhaps the simplest error correction code is the repetition code. And in this case, I take digital information as 0 and I encode it in 3 zeros. I take a 1 and I encode it in 3 ones. And now if I send that digital word, let's say 111, through my communication channel, and I lose one of my bits, let's say a photon was scattered from the signal, the result I'll get at the end would be a 101 instead of a 111. But now by looking at majority ruling, I'll be able to recover the original word and go back to 111. So the principle behind this notion is that errors here have to move words to outside the code alphabet. So if the code alphabet was 000 or 111, an error moved my encoded information to outside the code alphabet, and then by performing a test, a decoding, in this case a parity check, would allow me to reconstruct the original world. In quantum information, we do the same thing. So instead of using a single qubit to encode a single physical qubit to encode one logical qubit, I use here in the repetition code 3 physical qubits to encode one logical qubit. Again, my superpositions now would be superpositions of 000 and 111, and I again represent them as a point on the surface of a unity radius sphere. Now, the idea is that now errors should again move me to outside of the code subspace into an alphabet, if you like, which is different than our error correcting code. But errors cannot rotate it. They cannot move the point on the sphere. All they can do is move my point to a different sphere to exactly the same location. Now, if all I measure later on is which alphabet my information is encoded in, I find out on which of these codes my information is, and I can reverse it and bring it back to my quantum error correction code. And using these methods, we believe today that we will be able to construct in the next decade or so, hopefully, a fault-tolerant, quantum error-corrected, large-scale quantum computer. Last week, Serge Rosenblum, also here from the Weizmann Institute, gave you a review of the different technologies that people use in order to build quantum computers. In Serge's lab, he uses superconducting circuits using nanowires at very low temperatures. In my lab, I've shown you before, we use laser-cooled atoms. Again, a picture of a quantum byte, if you like. People are using photons in order to build quantum computers. People are using semiconductor quantum dots. And there's probably another 5 or 6 more technologies which are used in order to try and realize a quantum computer. So to sum up, really the main points I wanted to bring across are the following. Currently, we have medium-sized quantum computers. They're still noisy, and therefore their operation is compromised. The community was able to show quantum advantage using these noisy quantum computers. So there was a demonstration of algorithms that are stronger than any classical possible attempts. On the other hand, we're still limited in performance. In the future, what we need to do is build fault-tolerant, large-scale quantum computers. And one point I wanted to bring across as well is that if you think of quantum computers, at the end of the day, what we're trying to do is create superposition of macroscopic objects. And if you remember, I told you that we believe that superpositions of microscopic objects do not happen spontaneously in the world. That is probably because these superpositions are exponentially more sensitive to noise, but that's okay. You know, Boeing 787 doesn't happen spontaneously in the world. You put a big group of talented engineers for 10 or 15 years, and they engineered this highly technological object. Perhaps the same is true with quantum computers. And we will be able to engineer a superposition of a macroscopic object, of a large object. And that really puts us in a win-win situation, because if we succeed, we actually achieve a new paradigm in computer science, and we bring to the world a disruptive technology that would really change the ability of computers to solve problems of interest. However, if we fail, and we fail not because we haven't tried hard enough or because we were not sufficiently creative to find good technological solutions, but because physics prohibits us from preparing macroscopic superpositions, that means that we would find new physics which is beyond quantum mechanics, and that would even be a larger revolution. That would be not a technological revolution, that would be a scientific revolution. And as we all know, scientific revolutions really bring behind them much bigger technological revolutions and a very big impact on our life. So that's it. And thank you for your attention. And I'd like to open the floor for questions.
Professor Ozeri, thank you very much. Now it's time for questions. Don't be shy. Please ask. Well, I think that
overwhelmed by quantum.
And my question is about the entanglement. How do you explain it? That one particles or one phenomena know at no time what's going on the other one.
So I think that we can't understand it because we don't really understand, if you like, the ontology of what's going on. We don't understand the inner mechanism of really what quantum measurement means. When you think about correlations in the classical world, things often correlate, right? If I correlate the flip side of two coins and I leave one coin here and I take another coin to a different place, and I'm not looking at the coins, and now I uncover the coins, they'll remain correlated. The strange thing here is that in quantum physics, I don't know the outcome of a measurement before I perform it. And now when I perform the measurement, the coins remain correlated regardless of what I choose to measure. And that's really counterintuitive and surprising. And I think the root to that surprise is that we do not really understand what happens when we measure. So measurement is still an open physical question. So.
Okay, you have a few questions on the Q&A. Would you like me to read it, or you can read it?
I can open it. So David Fish is asking, is the scale of an atom in one of your first slide really 1 millimeter? No. So if you look at my slides, so what you see here, for example, is an array of 8 atoms. The distance between atoms is a few micron. And the reason you see each one of the atoms is about 1 micron is because my imaging system, my microscope, only has a resolution of about 1 micron. The actual size of an atom is roughly 1/10 of a nanometer. So 10 to the minus 10 meters. Benner Herman asked, does God exist? Wow. I think I'm not the authority to answer this. I'm sorry. Ricky Hehe says, was there an experiment that showed that EPR was wrong about entangled states? Yes. So up to the mid 60s, it was not a physics question, but rather a metaphysical question, because there was no way to check whether EPR is right or wrong. But in the mid 60s, a physicist by the name of John Bell came out with a statistical criteria that would check whether EPR are right and quantum superpositions are wrong, or quantum superpositions are right and EPR is wrong. That statistical test is called Bell's inequality. And today, Bell's inequality has been measured without any loopholes and with a statistical significance of many, many standard deviation. So we know today that Einstein, Podolsky, and Rosen were actually wrong, and quantum mechanics is correct. Oded Ben David is asking, realistically, when do you think we'll have a real 100K qubits computer? That's a difficult question. Prophecy is given for fools. But I think, if you look at the development today, I think that we see computers which consist of hundreds of qubits. We'll see thousands, or I should say tens of qubits. I'm sure we'll see hundreds of qubits in the next 2-3 years. Going beyond hundreds to thousands would only make sense if we contain quantum error correction and perform fault-tolerant quantum computing. I believe that it'll take probably a decade to reach the point where we stabilize quantum computing against noise. But I think that a decade from now, there's very good likelihood that we'll see quantum computers that are fault-tolerant and error-corrected. And at that point, going from 1,000 qubits to 100,000 qubits, I don't think that would be a big deal. It's really a modular type system. Roy Wolf is asking, can you explain the limitations on communication through interference? For example, interfering with an entangled particle and sensing interference to transfer information at a different location. So I'm not sure. So you're asking either on communication channels that are using entanglement or communication channels that are using interference. Let's speak about entanglement because that's more quantum, if you like. So the advantage entanglement brings to communication is the ability to distribute keys in a very secure way. If two quantum systems are entangled, that means they're correlated. If I measure them at one place, I know immediately at the other place what the key is, and therefore you can transfer keys in a very secure way. So communication using entanglement is very useful if what you want to do is use good secure cryptographic systems. David Fish says, so it's probably a typo. Please see previous images you presented. Okay, I think now when I think about it, I think what David wanted to allude to is the interference of atoms here, which said 1 millimeter. So David, what you see here, what 1 millimeter is, these interference fringes are the wavelength of the atomic wave function, which means that the atom is delocalized over a millimeter, but if I'll measure the atom, I'll find out that it's a 1/10 of a nanometer object. So again, it's like in the interferometer that I've shown you, the size of a photon, I don't know what the size of a photon is actually, but the uncertainty in the delocalization of the photon, the uncertainty in its position is 1 millimeter. But when I measure the photon, I'm going to get a very small click on a detector here and a very small click on a detector there. So the wave character of the photon can be distributed over a distance which is much larger than the photon size or the atomic size itself.
I think we have only time for one question and not more, because you have to leave on 6. So
yeah. So I'll read one question. Tali Septon, thank you very much. Error correction, how much is engineering and how much is fundamental? Also, are you and your students working on combining classical and quantum computation in a circular manner? So the answer is yes, and I think quantum error correction is right at the border between engineering and fundamental. So, part of our work is to engineer better quantum error correcting code and implementing them. Part of the question is, what are the fundamental physics phenomena that are behind this quantum error correction code? So it's really in the borderline. And are my students working on combining classical and quantum computation? Yes. Some of the quantum algorithms that we work with, not just us and the community at large, are called hybrid quantum computing. A lot of them come from the world of optimization. So if you're trying to find the global optimum of some NP-hard problem, what you could do is try and run some quantum algorithm that would give you an answer. Then you change the parameters of your quantum algorithm by using a classical optimization protocol, and then you do it vice versa. One example for such an algorithm is called QAOA, so quantum approximate optimization algorithm. And I encourage you, Tali, to go and read a little on it. So we certainly are working on hybrid quantum algorithms.
Professor Ozeri, thank you very much. I'd like to thank the audience as well. And I hope to see all of you in the next lecture. And Ozeri, you too.
Thank you very much, Shlomo. Have a good evening.
Good
Cheers.
evening.
Bye-bye.